Hello there, Mr. Sutton here, bringing you the Algebra 2 6-4 lesson on transformations of exponential and logarithmic functions. That's a mouthful. We've got two parts for this one which we'll be spending on the exponential, the other which we'll be spending on the logarithmic. And specifically, we're going to be graphing and writing transformations of these two different types of functions. So we're just going to dive right in and see if we can graph one of these exponential transformations. We're starting with the f of x function, which is 1/2 to the x, and the g of x function is basically that minus 4. We want to describe the transformation represented by g and then graph it out. Well, what transformation is happening? Since we're subtracting 4 outside the original function, it's the same rules we've been following for every time we do transformations. Outside changes are up, down, and they are exactly what they look like. So this is a translation of down 4, a shift of down 4. And just as a little review, changes that are happening inside the function, which for exponential functions means inside the exponent, those changes are left-right, they're horizontal, and they're the exact opposite of what it looks like they're doing. So we've got our kind of an idea of what this function is going to be doing. How do we actually graph it out? Just like before, we're going to start with a parent table, and then we're going to change the x and y rules, get a new table, and then just graph the points in the new table. But the tricky part about these exponential functions is that there isn't just one parent function. There's actually, I guess, a different parent function for every single base, like this 1/2, that you could have. So how do we deal with this? So what we're going to do is we are going to create a parent table for the specific base that we're dealing with. And then using that new parent table, we're going to create some transformed x and y rules. Now for your parent table, you could use -2 through +2, but that's kind of overkill. It turns out for growth functions, functions where the b value is bigger than 1, you can actually get away with just using x equals -1 to +2. You don't need -2 in there. And for decay functions, like the one we're dealing with here, you can get away with just using -2 through +1. Now the reason that I'm not including that fifth point is because it doesn't really add a whole lot of information to the shape. Just using these 4 points here, you're going to have enough to graph this out. And just remember, with exponential functions, you also have that horizontal asymptote that is normally on the x-axis. So with all this in mind, see if you can create this new parent table, transform it, and regraph it. All right, let's see how that worked out for us. So we have f of x. Since this is decay, I'm just going to be going from -2 to +1. I mean, if you included +2, not the end of the world. It's just kind of more work than you need. So -2, if I plug that in here, that's going to be reciprocal of this to the second power, so 2 squared, which is 4. 1/2 to the -1 is 2. Anything to the 0 is 1. And finally, 1/2 to the 1 is just 1/2. So this is what we're going to be transforming now. Taking a look at our transformations, since we're not affecting the inside of the function at all, the x's are just going to stay the way they are for this g function. But since we are going down 4, that means we have to do y minus 4 for the y rule. So the x's just remaining -2, -1, 0, and 1. For y, we're subtracting 4 from all of these. So 4 minus 4 is 0, 2 minus 4 is -2. 1 minus 4 is -3, and then we have 1/2 minus 4. You could call that -3.5 or -3.5, however you want to conceive of that. So we can get by with just a regular kind of x and y axis going from 6's in every direction here. So just graphing these out, we've got -2, 0 right there, -1, -2, 0, -3, and finally we have 1, -3.5. And remember, we have normally a horizontal asymptote on the x-axis. That's getting shifted down 4 because the whole thing's getting shifted vertically. So the rule here with these asymptotes is you have to draw the asymptotes that are not already on the axis. And we can represent those with a horizontal dashed line for this one. So just graphing that out using our standard decay exponential shape, it's going to look something like this. And there we go. All right, let's try another one here. Pause the video and give this one a shot. This one's a little bit tricky. All right, so first describing our transformation, we've got, let's see, this 3x minus 5 happening inside the exponential function, inside the exponent. So this is going to be a horizontal change. Now, what is happening horizontally? Well, we see multiplication by 3 and subtraction by 5. So there's going to be a horizontal shrink because it's opposite of what it looks like. We're also going to be translating right 5. But here's the tricky part. Which one of these happens first? Normally, because of PEMDAS, we would think that the shrink is happening first. But in fact, because this is inside the function, it's even opposite PEMDAS order. So the first thing that happens is actually the translation, and then that's going to be followed by the shrink. So let's write that down. Translation 5 units right, followed by a horizontal shrink. And that's going to affect how we write out our rule. Now let's create our parent table for 3 to the x. So we've got, this is growth, so we're going to be going from -1 to +2. So we have 3 to the -1 is 1/3, 3 to the 0 is 1, 3 to the 1 is 3, and 3 squared is 9. Now for the rules here, because we have the translation happening first, we're going to have x plus 5 inside a parentheses, and outside we're going to be multiplying by 1/3. And then for the y, nothing's happening outside the function, so we're just going to leave y the way it is. All right, so let's change all of our x values now. We have -1 plus 5 is 4 times 1/3 is going to be 4/3, or 1.33 if you want to make it a decimal, make it a little easier to graph. And then if we plug 0 in, I've got basically 5/3, or 1.67. If we plug in 1, we've got 6 times 1/3, which is an even 2, which is kind of nice. And 2 plus 5 is 7, times 1/3 is 7/3, or 2.33. And the y's we said were staying the same. I'm going to rewrite this 1/3 as 0.33, and then the rest are going to be exactly the same. All right, so graphing all this out, my x values are kind of small relative to how they usually are. It's very compact here, so I'm going to make my grid lines go by 0.5s just to be able to fit this a little bit better. So I've got 1.33, which is roughly here, comma 0.33, so about here. And then 1.67, comma 1. And then we've got 2, comma 3. And then finally 2.3, comma 9 all the way up here. And because we didn't shift this vertically at all, the horizontal asymptote is still on the x-axis, so we don't need to redraw it. We'll just draw a function with that asymptote growing exponentially. For our final exponential graphing transformation for this part of the lesson, we're going to throw e to the -x at you. So pause the video and see what you can do with this. And when you're making your x and y values, feel free to round it off to 2 decimals. All right, give it a shot. So the transformation happening here, since we have a -1/8 happening outside, this is going to be a vertical shrink and reflection. And you might be tempted to say we have a horizontal reflection because of the -x here, but you'll notice that the original function had a -x as well. So you could think of this as e to the x with a horizontal reflection if you wanted, or you could just leave it like this. Anyway, let's do our parent table. So that's going to be e to the -x that I'm using. And since this is basically 1 over e to the positive x, my b value is going to be between 0 and 1. So this is decay, meaning I'm going from -2 to +1 if I'm being a little lazy with my parent table. And I'm going to go to the calculator immediately to actually get some approximate values of these. Otherwise, I have no idea what things are in terms of e on the graph. All right, so let me plug -2 into this function to start with. And let me just to make my life a little easier, I'm just going to make a function out of this so that I can just plug things easily into it. So we have -x there. And now let me do just f of all these things. So f of -2 comes out to about 7.39, and then f of -1 about 2.72, which is basically e. And then let's see here, this is e to the 0, which is just 1, and we have e to the -1. Let me just plug that in here. That's about 0.37. So what transformation are we doing? There's nothing happening horizontally to the parent function that they've given here. So I'm just going to leave this x the way it is. For the y values, since we have this negative 1/8 being multiplied outside the function, that's what I have to multiply by y. So my x's are staying the same, just negative 2, negative 1, 0, and 1. For the y values, I have negative 1/8 times all of these things. So let me go ahead and just do that on the calculator. So let's see here, negative 1/8 times, and now we'll do 7.39. That comes out to 0.92. And then let's put 2.72 in there. Just a lot of calculator work on this one, but sometimes that's the way it is. So negative 3.4 exactly, although I did round off that original. And if I plug negative 1 in there, well, that's just whatever negative 1/8 is as a decimal, so we'll call that negative 0.13. And then finally plug in 0.37, and that comes out to about negative 0.05. So pretty small value there. All right, so I'm making my x values go by ones. My y values, these are tiny y values here. So I'm going to make those go by like 0.1s. And I'm mostly in the negative territory here because of all these values. So we've got negative 2, comma negative 0.92. That's somewhere down here. And then negative 1, comma negative 3.4 is roughly here. 0, comma 1.3 negative is about here. And then finally we have 1, comma negative 0.5, or 0.05 rather, which is about halfway between there. Now for the horizontal asymptote, we didn't shift things vertically at all, so we still have y equals 0, the x-axis, for a horizontal asymptote. The difference, though, is that now we're going up into that instead of down into that. So here's the shape of this curve. And if you're wondering, is this a true exponential function at this point, I guess technically it wouldn't, because the a value is not supposed to be negative, but we can still graph it and transform it. For this problem, they want us to write a rule that represents the indicated transformations of f of x equals 2 to the x. So they want us to do a reflection in the x-axis followed by a translation 4 units right. So just like we've been doing on these types of problems, it's a good idea to do each transformation by making a single new function for each of these instead of trying to do it all at once. And again, just keep in mind that horizontal changes, inside changes happen inside the exponent. Outside changes are going to happen outside of this 2 to the x. So pause the video and see if you can write a transformation for this. All right, so let's handle the reflection in the x-axis first. That's a vertical reflection, so I'm going to make a new function, the g function, that's just going to be negative f of x. And just replacing f of x with 2 to the x, that's going to be negative 2 to the x. Next up, to go 4 units right, I'm going to create an h function that is basically the g function but translated 4 units right. So since it's left-right, it has to go inside, so I have to do h of x equals g of x minus 4. It's opposite of what we expect. And inside the function means inside this exponent here. So this is going to be a negative 2 to the exponent of x minus 4. And that's it. All right, so at this point we have reached the end of part 1 of this lesson. We're done talking about exponential functions, kind of, sort of, for the rest of this one. Pause the video, give some of those graphs and writings a shot, and then join us when we come back to deal with graphing logarithmic transformations. Hello there, welcome back if you're rejoining us. This is part 2 of our lesson on transformations of exponential and logarithmic functions. In this one we're dealing with the logarithmic functions. Before we try to transform these, though, let's just see if we can graph one that's not being transformed, because that's a little bit of a task if you've never done it before. So the way that we're going to approach this is we're going to take advantage of the fact that logs and exponential functions are inverses. If we can graph the exponential inverse version of this function, then all we have to do is switch all the x and y values, and that'll give us the logarithmic version. So again, my strategy is for log base b of x, I'm going to create a parent table for the exponential function b to the x. And then I'm just going to switch all the x and y values to get my log table. So see if you can do that. Pause the video and try that with this base here, base 3, and then we'll see how you did. All right, so let me start by creating a table for y equals 3, base 3 to the x. And because this is growth, because my b value is bigger than 1, I'm just going to go from -1 to +2. So plugging all those in, 3 to the -1 is 1/3, 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9. And again, I'm just going to switch all the x and y values for my log version of this. So I'm going to have x values of 1/3, 1, 3, and 9, and y values of -1, 0, 1, and 2. So there's my log table, again, just switched x and y. Now I can just graph all this. And I'm going to make my x-axis go by 2's because I have to make it all the way up to 9 here. So we've got 1/3, comma, -1, right about there. 1, comma, 0 is here. 3, comma, 1 is up here. And 9, comma, 2 is up here. Now before we try to graph this whole thing, we might be wondering, is this thing going to go to the left of the y-axis? And it turns out that there is a vertical asymptote for all of these regular unshifted log functions at x equals 0 on the y-axis. So let's graph that out, and then we'll talk a little bit more about why that is. No pun intended. So here is our graph using that vertical asymptote out over there. Now, why is there a vertical asymptote there? I mean, we can see that there is if we graph enough values, but it's good to know why. Part of the reason, one way you can think about this is the inverse of 3 to the x. 3 to the x is an exponential function that looks something like this. It has a horizontal asymptote on y equals 0, the x-axis. So if you flip all that over the line y equals x, then your horizontal asymptote is now becoming a vertical asymptote. So that's part of the reason. Another way you can think about this is telling us that the domain of these logarithmic functions is actually going to be all positive x values. The range is going to be all values, all possible y values, all real numbers, but the domain is limited to positives. Because if you think about it, when you plug a 0 into this log function, you'd be asking would I have to raise 2 to get 0, which would be impossible. If you plugged negatives in here, you also can't get a negative number by raising a positive number to some power. So for that reason, it's worth noting the domain and the range of these logarithmic functions. And again, that's a domain of x greater than 0 and a range of all reals. For this next problem, we're going to be transforming the log function. And just as a little bit of a hint here, that is log base 10, but you already knew that. That's the common log if you don't see a number down there. Pause the video, and we're basically going to handle this like the exponential transformations, only you're going to have to, do the inverse graph, the parent table, then the parent table for the log function, then you're going to have to transform that. So you'll have a total of 3 tables when all is said and done on this one. Pause the video, give it a shot. All right, so let's start with representing the transformation that's going on here. Since I have this -1/2 inside the log function, that's going to be a horizontal reflection and a stretch by 2 horizontally. So horizontal stretch and reflection. Now let me do my parent table for 10 to the x, because that's the inverse of log base 10 of x. So I'm going to be going from -1 to 2, because again this is growth. So -1 plugged in here gives us 1 over 10. 10 to the 0 is 1. 10 to the 1 is 10, and 10 squared is 100. Now for the inverse graph of this, log of x, that is going to just be all the x and y values switched. So everything that was y is now x, and vice versa. Now for the transformed table on this, we're going to be multiplying the x values by a -2 to represent this transformation. So we have -2x. Nothing's happening outside the function, so y is staying the same. So we've got negative 2 times 1 over 10, which is negative 1/5, or negative 0.2 if you like. Negative 2 times 1 is negative 2. Then we have negative 20 and negative 200. And then the y values are still negative 1, 0, 1, and 2. So we have to make my x values go by, I don't know, 40s, 20s, something big in order to accommodate these values. And we're going to be mostly to the left of the y-axis. The y values can kind of stay the way they are. So I'm going by negative or positive 20s, whatever, 20-degree increments here. So we have negative 1/5, which is really tiny, very close to the y-axis, and negative 1, so somewhere down there. Then we have negative 2, which is also still pretty close, and 0. Then we have negative 20, it's a little easier to see, and positive 1 right there. And finally, negative 200 and positive 2. And our asymptote is still going to be x equals 0 because we have not shifted horizontally, even though we did some other left-right kind of stuff. So we're going to look something like this. Let's do one more logarithmic transformation graph just to make sure we've got the idea here. Pause the video and give this one a shot. So in terms of transformations, the +4 inside means we're translating left 4, and the 2 outside the log function means this is a vertical stretch. So vertical stretch, left 4. We're going to be using the 1/2 to the x parent function as kind of our starting point because our base is 1/2. So because we have decay, this is between 0 and 1 for the b value. That means we're going from negative 2 to positive 1 if I'm being a little lazy with my 4-point parent table here. Negative 2 plugged into this gives us 2 to the positive 2 exponent, which is 4. And then 1/2 to the negative 1 is just 2. 1/2 to the 0 is 1, and 1/2 to the 1 is 1/2. Now we're going to switch all the x and y values to get the log base 1/2 of x, f of x here. So now I've got 4 comma negative 2, and all the rest of these x's and y's are switching. And now to implement my changes, for the x values, I need to subtract 4 from all of those. And for the y values, I need to multiply by 2. So we've got 4 minus 4 giving me 0. 2 minus 4 is negative 2. 1 minus 4 is negative 3. And 0.5 minus 4 is negative 3.5. Multiplying my y's by 2, I've got negative 4, negative 2, 0, and 2. And let's graph all this out. I don't need to be crazy on my grid lines for these values. We've got 0, comma, negative 4 right there, negative 2, comma, negative 2, negative 3, 0, and finally negative 3.5, comma, positive 2 up here. Now, where's my asymptote at this point? Since I shifted left 4, that means my y-axis asymptote is now shifting left 4 as well. So I have an asymptote on x equals negative 4. And now let me just draw that curve here. So this looks something like this. For our last problem, we're just writing a rule that represents this transformation, just using a log instead of an exponential this time. Pause the video and see what you can do with this. All right, so for my first transformation, we have a translation of 2 units up. So I'm going to create a g function that's basically just going to be f of x plus 2. So that's just log base 1/3 x plus 2. Nothing crazy going on there. My next transformation is a vertical stretch by 2. So I'm going to create an h function that's essentially 2 times g of x. So that's 2 times all of this stuff here, which if I distribute it gives me 2 log base 1/3 of x plus 4. And with that, we are at the conclusion of this lesson. It's time for you to shift to your next activity in life. Feel free to get up and stretch. Until next time, Mr. Sutton signing off.